Solubility. Solubility of any substance is the maximum amount of that substance which can be dissolved in a specified volume of the solution at a particular temperature. So that's the maximum amount. The another way of defining it that it is the maximum number of moles of the solute which can be dissolved in 1 liter of the solution in order to prepare its saturated solution at a particular temperature. We know that once the saturated solution is prepared, no more solute can be dissolved. So that's its maximum possible solubility. That's why that many number of moles in per liter is called the substance solubility. And that is why solubility is always expressed in terms of moles per liter, in short called molarity. Solubility depends on the temperature. We know once we heat a saturated solution, it becomes unsaturated. So the solubility gets increased with the increase in the temperature because more of the intermolecular, interparticle spaces are created, and it decreases with the decrease in the temperature. Now, since in our syllabus we have mostly liquid solutions with liquid solvents, we have what the solubilities of the solids and the liquids in our syllabus. Let us first discuss solubility of solids in liquids. Solubility of solids in liquids. Like we can have NaCl in water. We can have any other salt in water. So these are the solids in liquids. The basic principle is like dissolves like. The solute, if a solute is a salt, is an electrolyte, is ionic in nature, it can easily breaks down into respective ions and gets what? Hydrated. It will be soluble in water or in polar solvents. If your solute is a non-polar covalently bonded solute, it will not be soluble in water or in polar solvents because it doesn't get broken down into respective ions and it doesn't get hydrated. It will be soluble in non-polar solvents like benzene, CCl4, carbon disulfide, etc. So that is why we have this common saying, like dissolves like. So in the polar solvents, we have the solubility of the ionic compounds, and in the non-polar organic solvents, we have the solubility of the organic salts. Like if we take camphor, it will not be soluble in water because camphor is organic. But yes, camphor will be soluble in organic solvents like benzene, CCl4, CS2, etc. So it's like dissolves like. First thing, the most important thing which is to be known to you. The second thing is, which actually one has to consider, is that the hydrogen bonding, because this is another important thing which creates exceptions. Like yes, we can have alcohols or we can have the other like species like phenol which can be dissolved in water. Why? Because they are able to form hydrogen bonding with the water molecules. So the another example type is that hydrogen bonding. We have to keep this thing in the mind in order to study the solubility of the solids and liquids. Now, after understanding the role of the nature of the solvent, how it decides the solubility of the solutes in the solution, and knowing the importance of the hydrogen bonding, let us move to the next factor which affects the solubility of the solutes in the solutions or in the liquid solutions. It is the temperature. Now, we know if the enthalpy of the solution is positive, it means the process of dissolving that solid solute in the solution is endothermic. Then always remember the solubility increases with increase in temperature. As the temperature is increased, the solubility will also increase because the process is endothermic. Whereas if the enthalpy of the solution is negative, that means the process is exothermic, energy is released when that particular solute is dissolved in the liquid solvent. In the process of forming the liquid solutions, the solubility decreases with increase in temperature. So this is most important. And then we also have another factor called pressure, but remember, pressure doesn't play much or any important role in deciding the solubility of the solids in the liquids. The reason being both these states are almost incompressible, so it doesn't make much difference. So this is how we can understand the solubility of solids in liquids. After understanding the solubility of solids in liquids, let us understand the solubility of gases in liquids. This doesn't actually, we normally doesn't get accepting, normally doesn't accept this fact that gases also gets dissolved in the liquids. The best example we can take is that if you can take a distilled water in a trough and you can place it in an open space for a short time, what we will find is that distilled water will automatically contain certain amount of oxygen dissolved in it. Now, from where this oxygen has come? This oxygen has been dissolved from the air due to the atmospheric pressure, which forces this oxygen to get dissolved in this distilled water. And this is how we get what? Aqueous oxygen in the solution. So the gas gets dissolved in the liquids and they form the solution, and their solubility was quantitatively first studied by Henry, and that's why it is decided by a law which is called Henry's law. The Henry's law states that the solubility of a gas in the solution is proportional to the pressure of the gas above the solution. So the solubility of a gas in the solution is, or the amount of the gas in the solution is directly proportional to the pressure of the gas above the solution. So we can write this as M proportional to P. This M is the amount of the solute or amount of the gas in the solution, and P is the pressure of the gas in the solution. And what we can the same law is also written as the pressure of a gas, or the pressure of the gas in the vapor phase is directly proportional to the amount of the gas dissolved in the solution. So we can write as P is proportional to M. This M is often expressed in terms of mole fraction. So we write this pressure of the gas is proportional to the mole fraction of the gas. We put G to indicate the gas, here also the G to indicate. So what is this mole fraction of gas in solution? And this proportionality is opened by a constant which is called Henry's constant. So this becomes KH xg, where this KH is called Henry's constant. We can take the example of a solubility of oxygen with the pressure. When we plot the graph of the oxygen gas along with its mole fraction in the solution, what we find is the graph comes out to be the straight line passing through origin, which indicates that the pressure is directly proportional to the mole fraction. So remember, the Henry's constant is, every gas is constant for every gas, and it is kH is proportional to the nature of the gas. Another important thing, that higher is the kH, Henry's constant value for a gas, lesser is its solubility. Because if you find out the value of the kH from here, it is pressure of the gas upon the mole fraction, which is how we express the solubility. Another important thing, the unit of mole fraction is always the unit of the pressure in which the gas is taken, because mole fraction doesn't have any unit. So the kH depends on the nature of the gas. Higher is the kH, lesser is the solubility, and its unit is actually the unit of the pressure of the gas taken. Now this Henry's constant is a very important law, Henry's law, which is very commonly used in normal day-to-day systems like our aerated drinks, cold drinks, in which the CO2 is actually dissolved under a high pressure. Or we can take the example of the scuba divers, which carries oxygen cylinders which are having helium. Now why they are having helium cylinders and helium and oxygen cylinders with them, not the pure oxygen or not the normal oxygen dissolved in the nitrogen? The reason is because if we take the normal air in the form of oxygen cylinders, what happens is the nitrogen have higher solubility in the blood under high pressure. Now that's because of which the moment these scuba divers or deep sea divers comes on the surface of the water, what they develop the bend problem. The same nitrogen which gets dissolved in the blood comes out in the form of the bubbles, and what they blocks the arteries and the veins and the capillaries and causes the bending problem. Now in order to avoid it, what we do is nowadays that we are having helium in place of nitrogen, which is having almost negligible solubility in blood even under a very high pressure. So the scuba divers, the aerated drinks, all are the examples of your applications of the Henry's law. Now you also need to know the effect of temperature. Always remember the solubility of gases decreases with the increase in the temperature, because then what happens is the kinetic energy of the molecules gets increased, so they escapes out more easily. So solubility decreases with increase in the temperature. So this is what is your Henry's law is, and this kH is your Henry's constant. Now let us understand the Henry's law with the help of a numerical. The numerical is Henry's constant for CO2 in water is 2 into 10 to the power 8 pascals. Calculate the solubility of CO2 in 500 ml of the soda water when packed under pressure of 4 atm at 298 Kelvin. So we are having, it is given that the Henry's constant for CO2 is 2 into 10 to the power 8 pascals, and the pressure in which the CO2 has been packed is 4 atm. Now we can convert this Henry's constant in terms of what? The atm from pascals. We know 1 atm is equal to 10 to the power 5 pascals approximately. So the Henry's constant becomes 2 into 10 to the power 3 atm, whereas the partial pressure of the CO2 is 4 atm. Now we know the formula. The partial pressure of the CO2 will be equal to Henry's constant into the mole fraction of the CO2 in the solution. So from here we can find out the mole fraction, which is going to give us the solubility of the CO2 in the soda water. Now we know it is like this. Now we know what is exactly the partial pressure of CO2 is. It's 4 atm. What is the Henry's constant is? It's 2 into 10 to the power 8, which is converted into atm as 2 into 10 to the power 3 atm into mole fraction of CO2 in the solution. So mole fraction of CO2 in the solution is 4 upon 2 into 10 to the power 3, which comes out to be 2 into 10 to the power minus 3. Now if this is the mole fraction, we know, which is very, very small, we know the molarity is 55.5 times of the mole fraction. So it is 55.5 times of the 2 into 10 to the power minus 3. This comes out to be 111 into 10 to the power minus 3. So it is 0.11 molar, or we have these many moles in 1 liter of the solution, and the question was in 500 ml of the volume. So, half of this. So, therefore, in 500 ml of the soda water, we will be having 0.11 divided by 2, which will come out to be 0.055 moles of CO2 is present. So, this is how we can find out the solubility or the amount of the gases in these solutions.